So our first talk is going to be given by Nosratullah Mohammadi. His talk is going to be titled Instantaneous Modulation of Gamma Rhythm by the Difference of Time Constants of Inhibitory and Excitatory Synapses.
Thanks, Adam. And thanks to Neuromatch organizers for giving me this opportunity to be here. Hello, everyone. My name is Nosratullah Mohammadi. Let me just share my screen. Okay, can you see my screen now?
Yep, we can see.
Great. Under this, I'm a master candidate at Institute for Advanced Studies in Basic Sciences, and under the supervision of Dr. Ali Reza Valizadeh, I studied the effects of changing synaptic time constants on brain rhythms, especially on gamma oscillation. So, why are we interested in gamma oscillations, and why we should even care how these rhythms are changing over time? Well, the answer would be that many studies on mammalian brains have observed the prominent existence of gamma oscillations during activities such as exploratory behavior in hippocampus and motor responses in premotor areas, and this list goes on and on. So those studies encourage us to find out, to dig in and find out more about the underlying mechanisms of modulation of gamma oscillation. So in this study, we chose integrate and fire excitatory inhibitory neurons as the building block of the network. We only focused on synaptic decay times of excitatory inhibitory neurons, and fixed all other parameters in each simulation. And due to simplicity, we chose exponential curve or function for postsynaptic current curve to just have more control over the parameters, and of course to get more, to increase our confidence about the results. So we created our network with 20% inhibitory neurons and 80% excitatory neurons with only 10% random connections. We simulated the network in a wide range of inhibitory synaptic decay time from 1.5 millisecond up to 3.5 millisecond, while we fixed the excitatory synaptic decay time to only 2.5 milliseconds. Previous studies showed us that increasing the inhibitory synaptic decay time would result in decreasing the gamma frequency. But other aspects of this change are left out. Here in this figure, you can see the power spectral density plot of one of the simulation with 1.8 millisecond of inhibitory synaptic decay time. So in order to study this effect, we have to first apply spectral regions. Sorry, to extract different spectral. In order to study, we have to first apply spectral separation to extract different spectral regions such as theta, alpha, beta, and of course gamma oscillation out of the total population activity. This can help us in future to study cross-frequency coupling such as phase amplitude coupling, which is basically that the phase of slower rhythms are going to modulate the amplitude of the faster rhythms. But what do we mean exactly by instantaneous modulation anyway? Well, we want to see if there's any meaningful correlation between the amplitude of the signal and the period of the signal in each cycle, meaning that if there's any, by knowing the amplitude of the signal, can we predict the period of the next cycle? And if so, how good we can predict it? And there are other terms such as the correlation between the period of each signal, each cycle, and the amplitude of the next cycles, and the autocorrelations of amplitudes as well as the period autocorrelations. So once we get the results, we can see that there are two different behavior in the simulation. In a smaller inhibitory synaptic decay time compared to excitatory synaptic decay time, those correlations that I mentioned are getting weaker by increasing the inhibitory synaptic decay time. But in larger inhibitory synaptic decay time compared to excitatories, those correlations are getting stronger by increasing the inhibitory synaptic decay time. And if we take a Pearson correlation coefficient, we can see that the results are nicely classified into two subgroups. And in terms of phase amplitude coupling between beta oscillation and gamma oscillations, we can see that in smaller inhibitory synaptic decay time, there is a considerable coupling, magnitude of coupling, and with a tendency to phase zero, right? And by increasing the inhibitory synaptic decay time to larger numbers, both the tendency and the magnitude of correlation, or the strength of correlations, are going to vanish. On the other hand, when we look at alpha oscillation and gamma oscillations phase amplitude coupling, the phase amplitude couplings is just going under phase shift from phase 0 to phase I by increasing the inhibitory synaptic decay time. And it is the same scenario for theta oscillation and gamma oscillations phase amplitude coupling. So the take-home message would be that there are different behaviors of amplitude period correlations, period amplitude correlations, as well as amplitude and period autocorrelations in two situations. And there is a phase shift in theta gamma phase amplitude coupling and alpha gamma phase amplitude coupling by increasing the inhibitory synaptic decay time. And last but not least, there is a decreasing of strength of phase amplitude coupling of beta oscillations and gamma oscillations by increasing the inhibitory synaptic decay time. And here I would like to thank my supervisor, Dr. Ali Rizadeh, who helped me and guided me throughout this project, and my wonderful teammates who didn't bother to help me whenever I needed. And now I'm open to your questions.
All right, thank you, Nosratullah. That was a really great talk. Some very interesting simulations there. So we have some time for questions. So if anyone's got questions, you can go ahead and post them in the Q&A or post them in the chat. I actually had a question. If you can go back to the phase amplitude or the phase coupling plot. Yeah, these three plots here. So I was wondering if I was somewhat surprised by the shift in phase amplitude coupling with the increase in inhibitory synaptic strength. Did that surprise you? And what, can you give me an intuition as to why that switch happens when you add more inhibitory, when you increase the time constant of the inhibitory synapse?
Well, I don't know the underlying reason for such phenomenon, because this is like one of the latest results of my study, and my next task is like going to answer these questions. This is a wonderful question, but yeah, I didn't see. I mean, as far as I know, I don't know any reason for such thing, for such happening, and yeah, I'm looking forward to answer those questions in future.
So what is the next step in order to answer that question? Have you kind of delineated that out? How you're going to interrogate that effect?
Yeah, like studying individual neurons would be would be step 1. So that like, yeah, observing like a bunch of random neurons, and I mean, observing those individually in either the voltage, the membrane voltage, and like the frequency of activity, and other, there are many, I mean, aspects that we can look and see.
Yeah, that's really interesting. Are they different populations of neurons that are actually driving the different components of the frequency? So do the neurons in your because these are simulated neurons, do you find very discrete populations as far as what's actually generating each of these components of the spectrum?
Well, due to, I mean, because of the parameters I set, and this is only one neural network, right? I mean, neuronal network. It is one balanced network, and those, I mean, all of these frequencies in different bands are happening in the same local network. And yeah, I didn't look at that area, like to focus on, I mean, those local regions, but that would be a great leap in the study, like see if there's anything going on there.
Yeah, it would be interesting to see whether you are, especially as you change the inhibitory current, whether you're creating distinct like how much you're differentiating different populations of neurons, and kind of what the dynamics of that whole system are.
Yeah.
There's a question that's just popped up in the Q&A from Caro. What was the composition of these EI neuron populations matched to any specific region of the brain? So is your study here meant to kind of be biologically plausible, if you will?
Yeah, that is a great question, because yeah, I mean, the parameters I chose is, I mean, from I guess CA3 region in hippocampus, and yeah, those are like typical parameters and the simulation that everyone do.
Sorry, I think we lost you for just a second. So you might want to repeat.
Okay. Sorry. So I told that, yeah, I chose the parameters from one of the simulations that happened on, I mean, simulate CA3 region in hippocampus.
Great, cool. So I think that's all the time for questions that we have, but that was a great, awesome talk. Thank you so much. And now we're going to move on to Zainab.